At the bottom of our cosmic hierarchy sit objects that shouldn't exist by any reasonable standard. Neutron stars pack roughly 1.4 to 2 solar masses into a sphere just 20 to 30 kilometers across. To understand this density, imagine crushing Mount Everest into a sugar cube. The atoms themselves have collapsed, with electrons forced into protons to create an ocean of neutrons pressed so tightly that a teaspoon of this material would weigh about 1 billion tons on Earth. These objects form when massive stars explode in supernovae, leaving behind cores that gravity has compressed beyond recognition. The surface gravity is 100 billion times stronger than Earth's, meaning if you somehow stood there, you'd be flattened to the thickness of a few atoms instantly. They spin at incomprehensible speeds, some rotating hundreds of times per second, creating lighthouse-like beams of radiation we detect as pulsars. What makes neutron stars worthy of this first level is their relatively modest cosmic scale. Yes, they're dense beyond comprehension, but they're still just city-sized objects. They represent the starting point of true cosmic extremes, the smallest members of our hierarchy, yet already pushing the boundaries of physics. The forces at work here are so intense that we still don't fully understand what happens in their cores. Some theorists suggest exotic states of matter exist inside, perhaps free quarks or strange matter that could convert ordinary atoms on contact. Neutron stars also mark the boundary between stellar objects and something more fundamental, a transition zone where matter begins to surrender to gravity's ultimate authority. They're stable, relatively speaking, but teetering on the edge of total collapse. This precarious balance makes them perfect anchors for our journey upward through increasingly extreme cosmic structures. When neutron stars fail to resist gravity's pull, they cross a point of no return and become stellar black holes. These objects range from about 5 to several dozen solar masses, with event horizons spanning just 15 to 100 kilometers. Unlike neutron stars, which are physical objects you could theoretically touch, black holes are pure gravitational collapse. The matter has compressed to infinite density at a singularity, surrounded by a boundary where space-time curves so severely that not even light escapes. Stellar black holes form from the most massive stars, those at least 20 times the sun's mass. When these giants exhaust their nuclear fuel, nothing can prevent the core's collapse. The implosion is so catastrophic that it warps the fabric of space-time itself, creating a one-way membrane in reality. Anything crossing the event horizon is lost to the observable universe forever, its information seemingly destroyed, creating what physicists call the information paradox. These black holes rank above neutron stars because they represent a complete transformation of matter into pure gravity. Where neutron stars still contain recognizable physics, black holes exist in a realm where our equations break down. General relativity predicts a singularity at the center, a point of infinite density and zero volume, but quantum mechanics suggests this can't be the full story. The truth likely requires physics we haven't discovered yet. What makes stellar black holes particularly unsettling is their abundance. Our galaxy alone contains an estimated 100 million of them, invisible gravitational traps drifting through space. Most exist in isolation, detectable only when they consume nearby matter or distort light from background stars. They're the universe's silent predators, patiently waiting for something to wander too close. At the hearts of most large galaxies lurk monsters that dwarf their stellar cousins by factors of millions or billions. Supermassive black holes contain anywhere from 1 million to tens of billions of solar masses, with event horizons large enough to swallow our entire solar system. The one at the Milky Way's center, Sagittarius A star, weighs about 4 million suns and has an event horizon roughly 24 million kilometers across, about 17 times the sun's diameter. These behemoths rank higher because of their profound influence on cosmic structure. They don't just passively exist, they actively shape galaxy formation and evolution. As matter spirals into them, it forms accretion disks that heat to millions of degrees, releasing energy across the electromagnetic spectrum. Many supermassive black holes launch jets of plasma at near light speed, extending hundreds of thousands of light years into space and pumping energy into the surrounding intergalactic medium. The formation mechanism of supermassive black holes remains one of astronomy's deepest mysteries. They existed when the universe was less than 1 billion years old, far too soon for them to have grown from stellar black holes through normal accretion. This suggests either they formed from massive seed black holes in the early universe, or matter collapse directly into them through processes we don't fully understand. Some candidates exceed 10 billion solar masses, like the black hole in the quasar TUN 618, estimated at 66 billion solar masses, with an event horizon spanning 2,600 astronomical units. These objects define the mass centers of their host galaxies. Stars orbit them the way planets orbit the sun, and their gravitational influence can be felt across thousands of light years. They're cosmic engines that convert gravitational energy into radiation and kinetic energy, fundamentally altering the chemistry and structure of their surroundings. When supermassive black holes feed voraciously, they create some of the universe's most luminous and extended structures. The quasar J05294351 hosts a black hole of about 17 billion solar masses that's consuming matter at a rate exceeding 1 solar mass per day. This feeding frenzy produces an accretion disk roughly 7 light-years in diameter, making it arguably the largest coherent disk of hot matter in the known universe. This level represents a qualitative leap from individual black holes to the vast structures they generate through their activity. The disk surrounding J05294351 spans about 15,000 times the Sun-Neptune distance, a swirling maelstrom of superheated gas, dust, and plasma orbiting at relativistic speeds. The temperatures in the inner regions exceed millions of degrees, causing the disk to radiate energy equivalent to 500 trillion suns. This makes it the most luminous quasar discovered, visible across more than 12 billion light-years of space. What elevates accretion disks to this level is their scale and energy output. They're not static objects, but dynamic systems where magnetic fields wrestle with gravity, where shock waves propagate through turbulent plasma, and where matter experiences conditions impossible to recreate in any laboratory. The disk's outer edges extend beyond what should be stable according to classical theory, suggesting exotic physics or magnetic effects we're only beginning to understand. These structures also serve as cosmic beacons, allowing us to study the early universe. The light from J05294351 began its journey when the universe was less than 2 billion years old, yet it remained undetected until recently because its extreme brightness made it appear star-like in surveys. It was hiding in plain sight, demonstrating how even our most powerful telescopes can miss obvious cosmic giants. Some galaxies extend far beyond their visible boundaries through enormous lobes of radio-emitting plasma. Alcyoneus stretches approximately 16 million light-years from end to end, while recent discoveries like Porphyrion span roughly 23 million light-years. These structures rank higher than accretion disks because they represent the largest known objects created by individual galaxies, exceeding 100 times the Milky Way's diameter. Giant radio galaxies form when supermassive black holes launch powerful jets that blast through their host galaxies and deep into intergalactic space. These jets, moving at nearly light speed, carry energy and magnetize plasma away from the central black hole. When the jets slow down far from the galaxy, they inflate enormous lobes that glow in radio wavelengths, creating structures visible across cosmological distances. The scale of these objects challenges our understanding of how long black hole jets can maintain coherence and how far their influence can extend. The lobes of Porphyrion required tens of millions of years to inflate, suggesting sustained jet activity over periods comparable to the evolution of life on Earth. The jets must have threaded through the cosmic web, pushing against intergalactic gas and dark matter, carving channels through space that persist long after the driving energy subsides. These radio giants also reveal something profound about galaxy evolution and intergalactic feedback. The energy they deposit into surrounding space can heat gas enough to prevent it from cooling and forming new galaxies, essentially sterilizing vast regions. They're instruments of cosmic regulation, black hole weather systems that affect structure formation across scales vastly larger than their host galaxies. Yet despite their size, they remain products of individual active galactic nuclei, which places them below the next tier of truly collective structures. In 2019, astronomers discovered a new class of cosmic phenomena, enormous faint rings visible only in radio wavelengths, often larger than their associated galaxies. These odd radio circles, or orcs, can span hundreds of thousands to millions of light years, and they represent a mysterious transition between galaxy-scale structures and larger cosmic formations. Orcs rank here because they're fundamentally different from radio galaxies. Rather than jets creating lobes, orcs appear to be expanding spherical shells or rings, possibly blast waves from extreme events in galactic cores. Recent observations detected X-ray emission associated with orcs, linking them to energetic processes in galaxy clusters. One particularly powerful example, RAD J131346.9, 500320, shows twin rings that may result from interactions between high-speed plasma jets and hot cluster gas, forming exotic plasma bubbles. What makes orcs especially intriguing is their uniformity and apparent abundance once we knew to look for them. They suggest that galaxies undergo periodic explosive episodes that can imprint spherical signatures on intergalactic space, signatures that persist for hundreds of millions of years. The physics creating these structures likely involves supermassive black hole mergers or extreme starburst events that drive super winds capable of shocking and sweeping up surrounding gas. These phenomena bridge individual galaxies and the cosmic web, revealing that black hole activity creates coherent structures far larger than the galaxies themselves. They're cosmic ghosts, remnants of ancient violence that have expanded to cosmological scales. Their discovery also highlights how much remains hidden in existing survey data. Orcs were invisible to optical telescopes and only emerged when radio surveys achieved sufficient sensitivity and resolution. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies embedded in enormous dark matter halos. These systems span tens of millions of light years and can contain total masses of 10 to the 14th or 15th solar masses, making them the building blocks of the cosmic web. The Phoenix cluster exemplifies this level's extremes. Located about 5.7 billion light-years away, it contains over 1,000 galaxies swimming in superheated gas reaching hundreds of millions of degrees. Its total mass equals approximately 1 quadrillion suns. At its center sits a supermassive black hole feeding faster than almost any other known, producing powerful jets that heat surrounding gas while simultaneously allowing rapid cooling and star formation at rates exceeding 500 solar masses per year. Galaxy clusters rank above individual galactic structures because they represent collective gravitational systems where dark matter dominates the mass budget. Roughly 85% of a cluster's mass exists as invisible dark matter, detectable only through gravitational lensing and galaxy dynamics. The remaining 15% divides between hot X-ray emitting gas and the galaxies themselves, with the gas outweighing the visible stars. These clusters serve as cosmic laboratories for studying dark matter, dark energy, and large-scale structure formation. Their abundance and distribution across cosmic time directly test cosmological models. The hot intracluster gas preserves a record of galaxy interactions, mergers, and feedback processes spanning billions of years. Clusters often sit at the intersections of cosmic filaments, where matter has streamed along the web's threads under gravity's persistent pull, making them hubs in the universe's largest networks. Beyond individual clusters lies the cosmic web itself, a vast network of filaments and walls connecting clusters across hundreds of millions of light years. Superclusters like Laniakea, spanning 520 million light years and containing roughly 100,000 galaxies, represent coherent flow patterns in this web, regions where galaxies move together toward common gravitational attractors. The Shapley supercluster exemplifies this level's scale, stretching 650 million light years and containing over 8,000 galaxies. Its gravitational influence affects galaxy motions across cosmological distances, including pulling on our own Milky Way from 650 million light years away. Inside Shapley, dozens of smaller galaxy clusters orbit within a larger gravitational framework, creating a hierarchical structure that traces the universe's matter distribution. Superclusters rank here because they represent the transition from bound structures to larger-scale patterns shaped by cosmic expansion. Unlike clusters, superclusters aren't gravitationally bound. They're expanding with the universe, but more slowly than the surrounding space. They trace the backbone of the cosmic web, the filamentary network that emerged from quantum fluctuations in the early universe, amplified by billions of years of gravitational growth. These structures reveal the universe's fundamental architecture. Maps of galaxy distributions show a sponge-like pattern with dense filaments surrounding vast voids, regions hundreds of millions of light years across, containing very few galaxies. This pattern reflects the initial density fluctuations from the Big Bang, filtered through dark matter's gravitational influence and dark energy's cosmic acceleration. Superclusters sit where multiple filaments intersect, creating nodes of enhanced density in the cosmic foam. The largest confirmed structures in the universe are giant walls and filaments stretching billions of light years, challenging theoretical limits on how large overdensities should grow given cosmic expansion and gravity's finite reach. The Hercules Corona Borealis Great Wall exemplifies this extreme, potentially spanning 10 to 15 billion light-years based on gamma-ray burst clustering at similar redshifts. This Great Wall ranks near the top because it appears to violate cosmological principles. Standard theory predicts structures larger than about 1.2 billion light-years should be extremely rare, as gravity and cosmic expansion limit overdensity growth. Yet the Great Wall may be 5 to 10 times larger than these theoretical limits, forcing astronomers to question whether large-scale uniformity truly holds or whether undiscovered physics operates at these scales. The structure was inferred from gamma-ray burst clustering, those ultra-energetic flashes marking massive star deaths. The burst showed non-random grouping at redshifts around 1.6 to 2.1, suggesting a wall of galaxies when the universe was less than half its current age. Recent analyses incorporating hundreds of bursts argue the structure could be 50% larger than initial estimates, potentially among the most extended known formations. What makes this particularly unsettling is the selection bias involved. Gamma-ray bursts are rare, occurring perhaps once per galaxy per million years. If the wall is detectable through such sparse sampling, its underlying galaxy distribution may be unimaginably rich. Some research suggests parts of the structure are closer to Earth than originally thought, implying even greater extent and complexity. These giant walls represent the universe's largest visible patterns, frozen imprints of primordial density fluctuations stretched across cosmological distances. They exist at the boundary between structure and statistical noise, challenging our understanding of cosmic evolution. The final level encompasses the observable universe itself, a sphere roughly 93 billion light-years in diameter containing about 2 trillion galaxies. This isn't just the largest object. It's the ultimate cosmic structure, the boundary between knowable and unknowable, between light that has reached us and light that hasn't. What elevates the observable universe above all other structures is its fundamental nature. It's not a gravitationally bound object or even a coherent structure in the traditional sense. It's a horizon, the limit of causal contact defined by light's finite speed and cosmic expansion. Everything beyond this boundary exists but remains fundamentally inaccessible, its light not yet having had time to reach us since the Big Bang. Inside this cosmic sphere is all of detectable reality. Structures from level 1 through level 9, every photon our telescopes have received, every gravitational wave our detectors have sensed. The edge shows us the cosmos as it was 13.8 billion years ago, near the beginning of time, when the first light traveled freely through space. Yet this presents a profound paradox. The universe is expanding faster than light, not because anything moves faster than light, but because space itself expands. Galaxies beyond a certain distance recede so quickly their light will never reach us, no matter how long we wait. The boundary isn't fixed. It grows about 1 light-year per year, but paradoxically, we lose access to galaxies as cosmic acceleration pushes them past the cosmic event horizon. Beyond our horizon might be infinite, containing infinite galaxies, stars, possibilities, or it may be finite but larger than we can measure. We exist in a small, illuminated bubble in something potentially boundless, forever unable to see the whole, forced to build cosmological theories from limited reality. The structures we've explored reveal a universe at the edge of comprehension, where the largest objects test fundamental physics and the very principles we use to understand existence. If you're curious about what else lies hidden in the cosmic darkness, subscribe to Cosmic Egg and check out this video next. Thanks for watching.